And welcome to Frontier Lab monthly webinar. I am Dr. Karthikeyan, Business Development Manager for Southeast Asia and India. And most of you know that Frontier Laboratories is a Japanese organization that manufacture the analytical pyrolysis system, also related accessories. And if you want to know more about Frontier Lab, please visit our website, www.frontier-lab.com. Okay, today, the topic for our discussion or sharing is actually Py-GCMS application in rubber and tire industries, where we will show the application related to product development or product conformation, reverse engineering, and failure analysis. Yeah, if you have any questions about today's topic or anything related to Py-GCMS application, please do not hesitate to post your questions in the chat box, or you can also drop me an email at karthik@frontier-lab.com. Okay, as we all know, like polymer, rubber also is one of the major commodity that is used in different industries. If you look at the annual average production worldwide, like this is the data I'm sharing from like 2000 to 2020, on average, we produce around like 9 million to like 11 million metric tons of this rubber. And there is a steady increase in like 2 to 3% every year. Okay, so that means we can see that so much of rubber is used in different industries. On the right side, if you see the global demand for elastomers, so again we can see the different type of rubber that is used in different industries and application. So if you look at the pie chart, like EPDM, the ethylene propylene diene rubber, or this polyisoprene or butyl isoprene, or this acrylonitrile butadiene rubber, and also the two type of SBR and butadiene rubber. So, but one thing you can see, almost like more than 50% of the usage is coming from this styrene butadiene rubber. Where are these rubbers used? The main application is actually the vehicle tires. Around 54% of global demand is attributable to this original, that means new purchase and replacement of tires. However, this material, this rubber material, is used in other products within automotive industry, like hoses, cables, seals, window and door profiles, even for these engine mounts and bellows for shock absorbers. So what we can see, the automotive industry is one industry where rubber materials are used in a big way. And other than automotive industry, it's also used in mechanical, electrical and electronics and construction industries. Okay, so it's used for conveyor belts, roller coverings, molded parts, and roof sheeting. So as we know, there are different type of elastomers, synthetic one. So starting from styrene, butadiene rubber, there's also like other type like butadiene rubber, butyl rubber, polyisoprene, and these are the things that is used in rubber industry. For other industries, it's EPDM, chlorobutadiene, and acrylobutadiene rubber. So what it means, the rubber materials are not just produced and used in any industry just like that. So the content or the chemical composition of this rubber is important to ensure that it is fit for the intended purpose. So if you look at this slide, okay, so again it's showing the rubber products used in different products in automotive industry and also in other industries. So you see the pictures of tire, rubber sheets, rubber kind of seal or O-rings, the diaphragm pump. So within car also like door seal, and tire also again it has like different parts within the tire that use a different type of rubber material. So what it means, varying the composition of rubber materials and different additives can influence the physical property and processability, which means the characterization of these materials are important. And today's webinar, we will show how the pyrolysis GCMS is used for characterization of rubber products or rubber materials. So the rubber material, the finished products always comes as like a rubber raw material plus some of the different additives that is meant for vulcanizing agent or vulcanization accelerator, activator, or antioxidant. So there are different materials that are used for these purposes. For filler, it's always carbon black or metal powder. For crosslinker, it is polyamines or polyols. For vulcanization, it's like amines or thiosols. For plasticizer, phthalates. But as you know, some of these phthalates are restricted under these RoHS. That means you have to choose that is not restricted. Also, you have to ensure that the concentration does not exceed the threshold limit of 1000 ppm. And again, for antioxidant, it can be like any type of aromatic amines or phenols. And anti-scoring agent is aromatic acids. So the chemical characterization of rubber materials is meant for determining the type of rubber used in the material, also the different type of additives present, based on which the quality of the material can be checked for the intended purpose. So how pyrolysis GCMS is used for this purpose is what you will learn from today's webinar. As you know, the thermal analytical technique is used for material characterization with different objectives. The most common and popular one is the TGA, thermogrametric analysis, which is mainly employed to determine the weight loss information of the material with the ramp temperature program. So this TGA data can tell you the temperature profile of the material. Similarly, the enthalpy changes is generally done with DTA or DSC, and mechanical change is done with dilatometry or TMA. Okay, when it comes to chemical analysis, most of the time it is evolved gas analysis. Evolved gas analysis, again, you can do it with different approaches and different objectives. What we have listed here, the evolved gas analysis can be done in like at least four common way. One is the pyrolysis GCMS, where it goes with the flash pyrolysis, followed by the GCMS, and thermal desorption, followed by GCMS, and UV, photo oxidation, followed by pyrolysis GCMS, and evolved gas analysis with MS. So these are the different way through which one can determine the chemical composition of the rubber materials. Then that can be used for product conformation or reverse engineering or failure analysis. Okay, just for the benefit of some of the participants who may be like trying to know about pyrolysis GCMS for the first time, so I'm just going to share briefly about the working principle, also the schematic. Okay, the pyrolysis GCMS is a hyphenated analytical technique that allows you to do the solid samples directly without any sample preparation. So the pyrolysis or the pyrolyzer is actually a sample introduction system where you are able to introduce the solid sample or liquid sample, and you can treat the sample at very high temperature, which is normally not possible with a standard GCMS equipment, because your inlet temperature is around like 300 degree, and you cannot introduce any solid sample unless you combine with some headspace accessory or aperture and different other equipment. So in this context, the pyrolyzer is also one kind of a sample introduction tool that expands the capability of GCMS for direct sample analysis. So how it works, okay? So you can see from this slide, the schematic is very simple. The pyrolyzer, basically a micro furnace. This is what Frontier Lab produced, but there are different type of pyrolysis system available where the pyrolyzer may be standing on the table, then you have a transfer tube to introduce your volatiles or the evolved gases from the furnace. But in our case, our furnace can be connected to the inlet directly. That means there are no transfer lines. So that means you don't lose any information or samples during the analysis because there is no transfer line. The compounds are directly introduced to the GC column. Okay, so this is one of the main advantage of our equipment compared to the other type of pyrolyzer. And secondly, you can treat the sample at very high temperature, so that allows you to do some of these macromolecules without any sample preparation. So when you treat the sample in this micro furnace, then the evolved gas, because your carrier gas of the GCMS is connected through the this pyrolyzer, the furnace. So that means the compounds that are released or like fragmented or break down from the parent compound will be pushed to the column for separation, then subsequently detected by the detector. So then you get output something similar to chromatogram, which we call it pyrogram, okay, because it is done through the pyrolysis. So the key advantages for pyrolysis GCMS, just in a layman perspective, you can do a direct sample analysis, and secondly, you can operate this microfurnace at high temperature, which allows you to do the polymer samples directly. Okay, let me just run through the steps through which this analysis is performed. So when you have any type of rubber material or any other polymer material, so you can transfer appropriate sample specimen into the sample cup. Then this sample cup is introduced into the pyrolyzer, where the temperature is set as per the requirement. Then when you start the analysis, this cup is dropped into the hot zone or the furnace, where it goes for either like breakdown or sometimes it's just releasing the additives. Then these compounds will be pushed, okay, through the help of carrier gas, and based on its retention capacity and partition coefficient, so you get these compounds are being separated one after other, then detected by the detector, then you get the output like chromatogram. Okay, so this is actually for analyzing phthalates in electronic material or plastic material. Okay, that's a small animation which again explains how this is done. So please watch this carefully. So when you have your sample, okay, this is actually kept in this sample cup, and when you start the analysis, please watch for the messages also. The sample cup is introduced into the furnace and sample is pyrolyzed or thermally dissolved. Then the compounds are pushing to the column, okay, with the help of carrier gas, where the separations are taking place. Then you can see these compounds are eluted or coming out of the column one after the other based on its retention capacity and its partition coefficient. So finally, you get to see multiple peaks. So this number of peaks represent the different compounds present in this rubber material or any other polymeric material. Okay. So this microfurnace has got different components. One is the sample introduction and followed by the furnace, then interface kind of transfer line, then the GC column and detector. Okay. Our multi-shot pyrolyzer can be used for 4 different analytical techniques based on the objective of your analysis. Okay, the evolved gas analysis is something similar to thermogravimetric analysis. In thermogravimetric analysis, you basically constantly look at the weight loss through like measuring the remaining sample in the furnace. Whereas in evolved gas analysis, you are not measuring the mass of the sample, but you are continuously analyzing the compounds that are evolved while heating the sample. So that's why it's called a wall gas analysis. So the output will be something similar to the TGA, but you have the temperature profile and the chemical information of the material from a wall gas analysis. Whereas in TGA, you will get to know only the temperature profile of the material. So a wall gas analysis is something we recommend to use it as part of your systematic the investigation. So that can lead to decide your next step for complete analysis. Okay, after a wall gas analysis, single shot analysis is another common technique, which is nothing but a flash pyrolysis. That means you take the sample at heat at very high temperature, then the additives and polymers are determined together. Okay, so you have one chromatogram that has all information. So where sometimes you may miss information because of a sensitivity issue or sometimes coelution problem and so on and so forth. So single shot analysis is something common, but it is not recommended for detailed chemical analysis. The other common approach that our customers employ is double shot analysis. In double shot analysis, basically you are doing two step analysis. First, you do the additives by thermal desorption, followed by the polymer analysis by flash pyrolysis. And a wall gas analysis hard cut is something is more like getting more data from one sample by thermally cutting the sample, okay, to different time zones. So later I will explain how this is. So this is something used for special needs like reverse engineering or failure analysis. Most of the routine analysis is generally carried out by double shot analysis or single shot analysis. Okay, now I'm just going to share different applications to address this product verification or conformation and some failure analysis. Also, the evaluation of photo, thermo, and oxidative degradation. Okay, the first example that I'm going to share is actually the characterization of tire materials. As we all know, the tire, a typical tire rubber, actually the tire is consists of rubber and additives. Okay, it's mixed in appropriate composition, then that leads to produce this tire. Okay. So if you look at the pie chart, it will have a natural rubber around like close to 40%, then synthetic rubber that can be around like 25%. Then you have this reinforcing material and also the other compounding agents. In rubber material, most commonly there are three type of rubbers. In tire, the three type of rubbers are used. One is the natural rubber, and the SBR and BR, butadiene rubber. So in terms of the additive, reinforcing material can be carbon black or silica. Okay. And compounding agents, vulcanizer, it helps to increase the elasticity of the rubber, and vulcanizing accelerator helps shorten vulcanizing time, and nucleating agent improves crystallization temperature, and anti-aging agent helps inhibits aging and degradation. It also prevents the surface cracking, and antioxidant prevents oxidation. So you can see that you use different chemicals along with this rubber to produce a final product like tire. And it is important to characterize thoroughly to ensure that right material in right combination is used for producing tires, good tires. Okay. So to analyze the tire, okay, so we basically want to show you that the tire is not just one single material. There are different material that are really compressed together. So usually we call it like bead, a sidewall, shoulder, and thread. So these are the different parts within the tire. So the thread helps protect the inside, okay, from the impact when it is like on the road. Shoulder dissipates heat during the driving, and sidewall protects the insides and prevents stretching. and bead basically help to fix the tire to the wheel. So the rubber composition varies depending on the part. So that's why if someone is interested to analyze the tire, it is not enough just you analyze the tire from any part of the tire. Okay? You have to have a specimen from different part of the tire. And this analysis can be performed by pyrolysis GCMS directly. That means no sample preparation. Okay, so we will just show one example. So we have collected one tire, okay, and we have separated sample from 4 different parts like thread rubber, shoulder rubber, sidewall rubber, and bead rubber. So we have taken sample around like 1 mm square small piece. Okay, we can use this cutter to really cut this sample, but we don't need a big sample mass for pyrolysis analysis. Pyrolysis GCMs basically it is always less than 1 milligram. Okay, so you have to take a right representative sample for your analysis. This data is actually the evolved gas analysis thermogram, okay, and the average mass spectrum. So this is what I was previously telling. If you look at, excuse me, just give me a minute. So if you look at the left side of this slide, okay, we have shown the EGA, the evolved gas analysis thermogram of 4 different samples. So this output is something similar to TGA, what you get, okay? At the same time, this data only tell you the temperature profile for additives and polymer. If you look at the right side, so this is actually the mass spectrum of this peak, okay? Because the output is generated through the mass spectrum, the MSD, the mass spectrometry detector. So you have this chemical fingerprint of the material. So this is something you don't get it in TGA. So that's why you have like additional information that is obtained through evolved gas analysis. Okay, so if you look at the mass spectrum, okay, and we also have a library that help you to even uh, shortlist the candidate chemicals of the material, okay, using this library, even at this evolved gas analysis. But you cannot complete the analysis just with evolved gas analysis for most of the time, okay. So this is only the preliminary information that you are getting to really shortlist the candidate material. So with further analysis, you are able to confirm that. Okay? But for some application, even the evolved gas analysis itself can give you the details of the sample. Okay? So the first thing related to additives and this mass spectrum can tell you what kind of additives present in your material. And the second one corresponds or represents the polymeric, the rubber, the polymers. So based on the monomer, you can tell what kind of rubber. Okay. So for example, thread has got SBR mainly, and shoulder has got SBR, but sidewall and bead has got butadiene and natural rubber. So this information you are getting even with evolved gas analysis itself. But with flash pyrolysis, you will be able to confirm, and also you can get the real composition of this mix or the blend. Okay, evolved gas analysis cannot tell you that how much is of butadiene rubber or how much is of natural rubber, but the flash pyrolysis can give that information as well. Okay, so after evolved gas analysis, you basically use the information on the temperature for single shot of flash pyrolysis. And what you see here is actually pyrolysis followed by GCMS. In EGA, okay, you are not using any GC column, so there are no separation. The separation, what you see as a 2P, is basically due to the temperature. So x-axis is temperature here, whereas in pyrolysis GCMS, it's after the thermal treatment of the sample, then the compounds are separated through the GC column, and each peak actually identified based on the retention time and the mass spectrum of the peak. Okay. So what we are able to see here, okay, the first sample has got this like thread is got SPR and NR, and second the shoulder also has got SPR and natural rubber, and side wall, okay, has got mostly the SPR. So this information, what we have observed in EGA, can be verified. At the same time, we can also tell the composition of this, which I will explain it later. Okay. Now, our interest is not only on the rubber composition, because even the rubber material performance can be altered or influenced by the different additives present in this material. Okay, so here I'm just showing one example how the additives can be even like measured quantitatively. Okay, here the objective is we just want to estimate the anti-aging concentration in different part of this tire. This anti-aging is actually N-phenyl 1,3-dimethyl-butyl phenylene diamine. Okay, in short, with the acronym, it's like 6-ppd. So this can be done by thermal desorption. Okay, so to do a quantitative analysis, you have to establish or create calibration for which you need the standard, right? So the standard is prepared by dissolving this PPD in dichloromethane, and initially you prepare a stock solution of the 0.5 milligram per ml, from where you can do further kind of dilution, or you take small portion of this concentrated stock solution and evaporate. That can lead to get absolute concentration of like 1 microgram, 2 microgram, and 0.1 microgram. Okay, so these are the three different concentration that we will use for establishing a calibration graph. So what you see in this slide is actually the pyrogram, okay, or basically we call it chromatogram. This is got through the thermal desorption GCMS. So you have only one single peak, okay, that corresponds to this 6 ppd, and that we confirm by this mass spectrum. Okay, so based on, so we have a library that can really match your peak and mass spectrum to the compound. Our additives database has got around like 600 additives, and polymer one has got 1,300 polymers. So it's a vast database. And all four different samples have been analyzed for this 6 ppd. So you can see they all show the presence, but the peak area may be different for different part of this tire. And so what we have done is we have created a calibration graph with three different concentration of this ppd, 0.1, 2, and 2 microgram. And using this calibration graph, we have also estimated, okay, for our samples the four parts of the tire. So you can see the area, like this is actually average from triplicates with the like 0.2 milligram sample, and you can see the area is different for different parts of the tire, and the RST also shown here. And this is the absolute concentration, and this is the actual concentration present in the sample. So you can see it can go as high as like 6,000 ppm inside wall, and as low as like 1,400 in thread. So this is something very important, okay, to get this composition in terms of the concentration, also to qualify the material for the intended purpose. Okay, so through this investigation, what we have obtained is the different parts of the tire, that the presence of rubber tag. Okay, thread has got SPR and natural rubber, and shoulder has got SPR and natural rubber. Sidewall has got butadiene and natural rubber. Bead has got like butadiene and natural rubber. So this is one information on the polymer side. So the other information is the presence of vulcanizing accelerator, fatty acid, anti-aging agent, and nucleating agent. Okay, all these. In particularly this project, they had a kind of objective to estimate this PPD, the anti-aging agent, so which was also accomplished. So that means we have done a kind of qualitative analysis for the presence of to know the type of rubber used in the different parts of tire and also the types of additives present in the sample. Then, in addition, we have also done the quantification or the quantitative analysis of this anti-aging agent in different parts of the tire. Okay, so that is one example for the product confirmation analysis. Now, most of these tire industries, they also have to do a QC, okay, based on this product confirmation test, where there are some ISO tests available. ISO 7270 has got two parts. The part one actually requires to look at the identification of polymers present in the tire, and the second part is actually is talking about the ratio, the composition analysis. So it's both are like same type of analysis, but first one is more like a qualitative, but the part two as for composition analysis of the blend. Okay. Then ISO 16038 actually, yeah, it's about identification of 32 anti-degradants. Okay, so I will show one example again how this is done. So you will see this is almost a similar approach what I have just shared. Okay. So we have taken this tire sample from car, truck, and bus. And again, within the tire, as we know, we have to take different parts of the tire to look at this composition. So sidewall, thread, and inner liner. Okay. So taking sample, yes, you use a cutter or sometimes this puncher, and the sample is introduced directly, okay, to get this. So this is done by this flash pyrolysis for determining the type of rubber material. But for additives, yeah, you have to do the thermal desorption. Okay. So what you see on the right side is the EGA, evolved gas analysis. It was produced or obtained by using this 300 microgram of sample, which is like 0.3 milligram. So you can see the pattern of this EGA thermogram is different for different parts of this tire. Okay. So some they have two peaks, some are like single peak, but again the tailings are different. That means the chemical composition of these four different parts within the tire are not same. Okay, but this information cannot be determined from the evolved gas analysis. You have to go for the flash pyrolysis or double shots. Okay, so this is the pyrogram obtained through this flash pyrolysis. Okay, pyrolysis temperature was kept at 600 degree. Then this is the chromatogram. So you can see the side wall has got butadiene and isoprene, and almost it's same for the thread from bus and track. So, but you can see even the thread for bus and track and car, sometimes they are different also, and inner liner is different also. Okay, so it's important to get this information to qualify the material for that particular usage. So based on the pyrogram, so now we were able to see the presence of different type of rubber within the tire. In sidewall, yeah, it has natural rubber thread also. You can see natural rubber is something used in all parts of this tire, but SPR is used only in like car thread and also the thread of the track. And this polyisoprene is generally used only in the inner liner, and butadiene rubber is used only in sidewall. Okay, so this is the information you are getting through this analysis. And yeah, this is not sufficient because you want to know the percentage of the composition. So you can look at this. Okay, again you have to initially produce this blend, okay, by mixing of these two in a known ratio, then use that information for doing unknown analysis of your sample. So here what we have done is we have mixed kind of a different known composition, and that has been analyzed by this technique, and you can see the theoretical value and the experimental values are in very good agreement. So that tells this flash pyrolysis can be used for composition analysis of the rubber blend. The second method is asking for determination of these anti-degradants, okay, in these SPR samples. So this is done by a thermal desorption. Okay, so if you want to know what is the condition that you need to use, that can be obtained from this wall gas analysis. Okay, so the thermal desorption is done at this condition from like 50 degree to like 320 degree, and this is what the data that you see. So there are two type of SBR sample have been analyzed for this application to show the the usability of this technique. And the first material has got three different type of anti-degradants, and the second one has got, yeah. So you can see they are not same. Okay, so it's also something that you need to be aware of. So you have to choose the right material with the right type of anti-degradant present in your sample. So this information can be obtained by the EG, the TD-GCMS, thermal desorption GCMS analysis. Okay, it's pretty straightforward. Okay, so I have shown the ISO method for two different objective or application. One is the composition analysis and also the type of rubber within the tire, and second one is determining these anti-degradants presence, okay, in different type of SBR samples. I was telling about the composition analysis. So here another application technical note that we have developed for the compositional analysis of blend rubber consisting of polybutadiene and polyisoprene and polystyrene. Okay, so you can choose the appropriate monomer for your quantification and confirmation. Okay, so in this case, yeah, you can use butadiene and isoprene and styrene, and you make a kind of blend with the different mixer, and you can show the linearity. That means this is applicable for this composition analysis. Again, yeah, we have prepared this mix at a different ratio, and we also looked into the relative peak area for this mixer, and this information is used, okay, for establishing the calibration graph. Then we have done some composition analysis of unknown sample, and we have found, okay, the ratio in terms of the starting material. That means this is what we have mixed and this is what we have observed. So you can see that you can use this technique for composition analysis of the blend rubber. Okay. Now we move on to another major objective of this analysis, which is actually, yeah, additives, because you always see the rubber, what type of rubber is in this material, but you can see that the influence is mostly got through the different type of additives present in the sample. All this is done by this thermal desorption. Okay, so here I am sharing one example, okay, where the analysis of free fatty acids in vulcanized rubber products, and particularly for certain type of analysis, you can consider this thermally assisted hydrolysis and methylation that can give a better selectivity and sensitivity. So for example, in this particular application, so we are interested in free fatty acids like stearic acid. So this stearic acid, if you are trying to do through a standard thermal desorption GCMS, you always have some issues due to pigtailing because of the polar nature of these fatty acids. And also it requires a frequent maintenance to keep the system clean, okay, because it's not totally like got rid of the column, so you may have some kind of background issue, so you have to clean the system very frequently. So to overcome this challenge, we can take a different approach. So instead of looking at the fatty acids directly, you do this thermally assisted methylation, hydrolysis and methylation. Then you actually look at the methyl ester. It's something similar to FAME analysis, okay, that is done for free fatty acids. So you can see, okay, on left side, this is the direct thermal desorption, and where you can see the peak has got this tailing. So that means your precision from this will not be as high as required. On the other hand, if you do this thermally assisted hydrolysis and methylation, it's the same analysis, then you have very clean peak. Okay, so that means your method, the data can be highly precise compared to the direct analysis. So this is one example where even these three fatty acids, the stearic acid in the rubber sample, is done through this uh, in situ hydrolysis and methylation using this TMAH, tetramethyl ammonium hydroxide. And we have shown the reproducibility because that was the main objective of using this hydrolysis and methylation. So what we have shown here, the methyl there are two kind of stearic acid present, palmitic acid and stearic acid. So in both cases, we have shown the RSD can be like less than like 5%. So for total free acids, generally it is a summation of both. Okay. So by using this hydrolysis methylation technique, you can really have good precision in your analysis. Now I'm going to flash few other applications, okay? And so you can always get this technical note from our website as well. Okay, here one example. Okay, again it's a antioxidant. Okay, so what we are trying to show through this application note or the technical note, you can have very good precision. Okay, you can also consider using this internal standard addition. Also, you can do it. Okay, so here the analysis of the NBR rubber. Okay, this acrylonitrile butadiene rubber sample for these antioxidants, and this sample has got two type of antioxidants. Okay, the NOCRA 810 is basically the phenyl isopropyl phenylenediamine. The NOCRAC 6C is actually N-phenyl 1,3-dimethyl butyl phenylenediamine. Okay, so the analysis confirmed the presence of both antioxidant, and also the reproducibility has been tested by 8 replicates, and the overall RSD is just close less than 2%. Okay, so this is just another, the previous one was anti-degradants and this is antioxidant. So again, yeah, we just show the thermal desorption GCMS analysis for such additives analysis and also show the reproducibility of the technique. Okay, this is another application for this analysis of compounded rubber, again for both actually the additives and polymer. Okay, so when you wanted to analyze the additives and the rubber or the type of rubber or the polymer, then we always recommend to go for a double shot. So the first step is thermal desorption and second one is the pyrogram. So how do we know these conditions need to be used? Okay, that is generally obtained from this evolved gas analysis. But we also have a general recommendation where you can do it without doing the EG also, but that is more like a shortcut. But this is something you may not want to do it when you are really looking for every minute information. Okay, so most of the time your thermal desorption condition will be something like this: 50 to 300 or 100 to 300, 20 degree per 20 degrees C per minute is a ramp. And after that, the GCMS will tell you what kind of different additives present in your sample. In this case, yeah, you can see the 2-methyl thibenzothiazole and mercaptothiabenzothiazole, then also this antioxidant and plasticizer also. And in pyrogram, you can see the isoprene and butadiene rubber, okay? And so that's what you are basically getting in the thermal desorption, all types of additives, and the flash pyrolysis, you are getting the polymer information. Okay, this is another application, again emphasizing on the additives, identification of unknown anti-degradant in rubber. Okay, so here what we are trying to show, because some of the time you do not know what is the anti-degradant that is present in your sample. Unless you have this information, your standard library cannot be used. So we have a library database for additives which has got around like 600 these additives. So using this database, you are able to analyze the kind of any type of rubber material for unknown anti-degradant. So this is what you are getting through this analysis. Okay, so in this case there are 3 peaks identified. Okay, and it also confirms, okay, the presence of this N-phenyl benzodiamine. Okay, and you can also even do the quantification by creating the calibration graph. So this application note just to show the use of our library for additive analysis. Okay, so that is pretty much on the basic product analysis or the product information or verification analysis, where we are trying to know or determine the type of rubber present or rubber consists in the material, and also the additives. This can be plasticizer, this can be antioxidant or anti like aging agent or regulating agent. So all this can be generally done, okay, or determined by using this double shot technique. So the first step is thermal desorption, followed by the flash pyrolysis for polymer. So this is what I have shown as one of the major kind of application in rubber and tire industries. Now, this technique has been widely used in R&D for reverse engineering as well as for failure analysis. So here I am showing one example of this failure analysis. Rubber material is used for this diaphragm pump. Okay, here we have a case where the diaphragm pump performance is been affected between 2 batches. Okay, the standard product should give like more than 1200 hours of performance, whereas one particular batch has got deteriorated even like less than 800 hours. So that means this product has got some quality issue. So we basically wanted to see what are the differences between this good and bad batch. Okay, so that can be the difference in polymer, the rubber, or it can be difference in the type of additives present. So it is pretty clear that this is what we wanted to know, but how we go about it, because it is a failure analysis where you cannot take things granted, so you have to go a systematic way. So the systematic approach is always start with a wall gas analysis, okay, from 50 degree to 700 degree at 20-25 minute ramp. So what you get is the EGA, the thermogram, wall gas analysis thermogram. And in this slide, we are showing the replicates, okay, just to show the reproducibility and also the pattern of this thermogram for good and bad patch of this rubber, diaphragm pump rubber. And you can see there are a few things obvious here. One is the peak top temperature for the polymer, okay, or the rubber is different by this 8 degree. That means the polymer composition between these two may be slightly different. And the second information what you see here, the good patch has got some additional peak at 335, which is not seen in this bad patch. So this can be the two difference that shows the product difference between this good and bad batch of this rubber. So with the single shot, you are able to see the difference in the polymer. Okay, so the good rubber shows two type of monomer. Okay, one is chloroprene, the other one is also the EPDM. So this is what two type of polymer rubber present consists in this good batch of this diaphragm pump, whereas the failed one shows only the EPDM. So this is very like obvious. So you have a product difference between the two, and that can be one reason for this performance difference. So similarly, we try to look at the hot cut. Okay, so as I said, you can have the detailed GCMS analysis of each temperature zone. So here we have done it for three zones, like zone A is 200 to 300, zone B is like 320 to 350, and zone C is 460 to like 520. Okay, so you can see there are certain antioxidants that is present in one but not in the other one. Then also there is a concentration difference on these hydrocarbons, and that is another major observation you have seen. So we have seen obvious difference between the product in terms of the rubber and the additives. So we have summarized this. So you have a product difference for this good and bad. So that we see. The bad rubber has got only the EPDM as a rubber, whereas the good material is just a combination of EPDM and chloroprene. Okay, and the second one is the additives. Also, again they are different. So you have the good one has got these free fatty acids, which we did not see in the other material, and hydrocarbons also there are like more and less. So this information is useful for the customer when they like procure the raw material for making the diaphragm pump. So they can have this as a criteria to look for the presence of EPDM and chloroprene before they can use this for constructing this diaphragm pump. So this is how the pyrolysis GCMS is used for failure analysis, product failure analysis. Okay, so I have one last example for this industry where EPDM, okay, ethylene and propylene diene copolymer rubber, okay, is used in automotive industry for door and seal. Okay, now you know that car is exposed to weathering or the different temperature when they are kept outside exposed to sunlight. So definitely the durability of this material is important. So one can even when people are using a different polymer for solar panel or any other external application, they have to look at the photo-oxidative degradation because it should not get degraded or oxidized in very short span of time. That means then your life cycle can be short. That means you have to replace more frequently. So for this reason, conventionally people use the weather meter or outdoor exposure. So these type of approach or investigations take longer period. On the other hand, we have a small accessory which is more like a UV probe, and this is an optical fiber with the UV light. So you can expose your sample with the UV light in the furnace itself. Then you can look at the compounds released during UV light exposure, or you can also look at the pyrogram after UV light. So one is this is fast. You can also get the information immediately compared to the conventional approach where you need longer time and large sample quantity. Okay, so how this EPDM need to be like looked for this photo-oxidative degradation because it is used in like making this door seal and also some of the liner. Okay, so what we wanted to show is this EPDM when you do this UV exposure, how it is behaving, and based on which they can qualify the material for this purpose. Okay, so you get three type of information from this photo oxidation degradation investigation. One is the EGA. So the evolved gas analysis tells you the pattern of this peak. So you have compared between three. One is without any UV light exposure, and another one is UV light with 10 minutes, and another one is UV light with 60 minutes. So it is evident the peak aperture height is different, okay, and also the peak tailing is different. So the UV light is really affecting the EPDM. Then it is important to evaluate whether this is good or we have to have a different brand of EPDM for our application. So the other one is the analysis of volatile degradation products. So you have thermal desorption study here. So initially you have your sample exposed to light, the air for 1 hour, then you see what is the compound that are being released at the 60 degree without any UV light. At the same time, you have 1 hour exposure to air at 60 degree with UV light, then you can see a lot of like additives being released. So this is what it shows that the degradation due to the photo oxidation. You can also do the pyrogram, okay, after the UV light exposure. So in this case, you can see without UV radiation, you have strong peak for the monomer of this propylene and also this butene, right? But as you have the UV light exposure, you can see these compounds are disappearing and you will see the increase in this CO2. And this is what? So that means it is sensitive to photo oxidation or the photo light or sunlight, and you can see the reduction of butene and hexane and also the increase in the formation of CO2, which tells the degradation nature of this EPDM. So this is another application where the pyrolysis GCMS together with UV light can be used for like quick evaluation of the photo-oxidative degradation characteristic of rubber material like EPDM. Okay, so with that, I would like to wrap up this session. So the short summary or a take-home message. Pyrolysis GCMS is a powerful tool for material characterization. Okay, so with different objectives in rubber industries. Okay, and it expands the capability of GCMS for direct analysis of polymeric material, which I said GCMS cannot do polymer directly because of the limitation on the inlet temperature. And direct analysis also allows you to like preferred approach for fast analysis and also minimize the time on analysis as well as contamination during sample preparation. And you can also do the analysis with micro amounts. And accessories like UV radiator and hot cut EGA really help you to collect every single information that is required for reverse engineering and failure analysis. Okay. So with that, I would like to thank you all for your kind attention. And if you have any questions, please post them in the chat box. I will try to answer them now.